Quench time. For a drink, right? No, I'm in a lab right now, and I'm looking at a detector circuit. A detector circuit that's been driven by a very high voltage source, and I'm looking for a picovolt. I'm actually almost looking for electrons themselves, one electron at a time, to hit that something detector and be able to see it. But I'm looking at I'm sitting on 500 volts already. It's enough to kill me. So, that detector sees something. It sees 10 somethings. Now it's sitting at 500.0007 volts. I have to quench that. I have to set it back to 500 volts. This is called a quench circuit. It takes a certain amount of time within the detector circuitry to do this quench and reset back to the detector circuitry 0, which is sitting on 500 volts. If I change that voltage to 600 volts, I increase the detector sensitivity. I also have concern about my quench circuit. Is it quenching quickly enough so that I don't overload the tube and possibly blow it out? Very big problem inside of photoelectric tubes. Not so much with Geiger-Müller tubes. Still, it can happen though. You can overwhelm the detector and the circuitry with counts. It's not really that hard to do. So in that, when you change that detector voltage, you have to consider that quench time because it's a part of the physics of the detector. We know about these detectors, right? We know about doing physical certifications on detectors, no matter what type of detector, right? We're just take that for granted in our conversation here. So that quench time, 500 volts, your wall voltage is 120 volts. The voltage on radar systems is in the megavolts. There's a peak envelope power in the gigawatts comes out of those radar sets. So quench time, we understand what that is. Kind of. In some rooms, in some specific places, we would talk to it. If we don't match the counting circuitry speed to somewhere within the quench time of the tube, we have a misalignment in our counting circuitry. So some people think about quench time, some people don't. Peace is out.